Do you believe the universe began with a single massive explosion? But what if that was a mistake? What if, instead of one beginning, the universe is being born from billions of tiny bursts scattered across space happening right now? What if gravity needs no mass, and dark energy is just an illusion? In today's video, you'll step into one of the most provocative theories of the 21st century, the Transient Singularity Theory. Welcome to Astronomy Universe. The journey to rewrite the history of the cosmos begins now. When we gaze at the night sky, it's easy to believe the universe is still, unchanging, and eternal. But within the scientific community, a quiet revolution began in the early 20th century that would reshape humanity's entire understanding of the cosmos: the Big Bang Theory. The Big Bang wasn't an idea that gained acceptance overnight. It emerged from a series of dramatic scientific discoveries. In 1927, Belgian priest and physicist Georges Lemaitre was the first to propose that the universe was expanding. Drawing from Einstein's general theory of relativity, he introduced the concept of the primeval atom, a singular point in which all matter, space, and time were once concentrated before it suddenly burst outward, giving rise to the universe. 2 years later, astronomer Edwin Hubble confirmed something astonishing. Galaxies are moving away from one another at speeds proportional to their distance, a groundbreaking discovery that served as the first direct evidence for an expanding universe. And with that, a profound question naturally followed. If the universe is expanding now, then in the past, it must have been smaller, denser, until it traced back to a singular point, the very beginning. Initially, the idea faced heavy skepticism. Even Albert Einstein rejected the notion of an unstable universe, adding a cosmological constant to his equations to preserve a model of a static cosmos. He would later call this addition the greatest blunder of my life. It wasn't until 1949, during a BBC radio broadcast, that the term Big Bang was first coined by a supporter, but by astronomer Fred Hoyle, who mocked the theory by referring to it as a Big Bang. Ironically, the nickname stuck and became the theory's most popular name. The turning point came in 1965, when Arno Penzias and Robert Wilson accidentally detected a persistent radio hiss coming from every direction in space. Unbeknownst to them, they had stumbled upon a critical prediction of the Big Bang Theory: the cosmic microwave background radiation, CMB, the ancient light left over from the universe's hot, dense beginnings. From that moment, the Big Bang Theory became the centerpiece of cosmology. More and more evidence piled on from the observed ratios of light elements like helium and deuterium formed during the universe's first few minutes, to the distribution patterns of galaxies echoing an origin from a single explosive event. The Big Bang was no longer just a hypothesis. It became a guiding framework for countless scientific missions, from the Hubble Space Telescope to the James Webb, from the Lambda CDM model to advanced computer simulations of galaxy formation. It laid the foundation for the modern worldview, one where everything began from a miraculous moment. But is that foundation unshakable, or is it hiding unanswered questions beneath its surface? We'll explore that further in the next chapter. Although the Big Bang Theory rests on a robust and consistent foundation of evidence, there remains a gaping hole in the model that science has yet to fill. That void is dark matter and dark energy. According to the widely accepted Lambda CDM cosmological model, ordinary matter, the stuff we can see and touch, makes up less than 5% of the entire universe. The remaining 27% is dark matter, which cannot be directly observed, and a staggering 68% is dark energy, an unknown force that appears to be accelerating the expansion of the universe. The paradox is striking. The two components that account for 95% of the universe's composition have never been directly detected by any human instrument. The concept of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky. He observed that galaxies in the Coma cluster were rotating so rapidly that based on visible mass alone, they should have flown apart long ago. But it wasn't until the 1970s that dark matter truly entered the mainstream of cosmology. Astronomer Vera Rubin, studying the rotation curves of spiral galaxies, discovered that stars at the outer edges were spinning much faster than expected, as if some invisible gravity was anchoring them. That force was attributed to dark matter. It emits no light, absorbs nothing, reflects nothing, but exerts gravity. Dark energy, on the other hand, is a much newer and even more mysterious discovery. In 1998, two independent research teams studying Type Ia supernovae as cosmic distance markers made a shocking discovery. The universe isn't slowing down after the Big Bang, it's accelerating. This was completely at odds with prior expectations. To explain it, physicists had no choice but to introduce a new, unseen entity into their equations: dark energy, a hidden repulsive force seemingly woven into the fabric of space itself. But after decades of searching, both dark matter and dark energy remain nothing more than ghosts in our models. No detector has ever captured a dark matter particle. No experiment has definitively confirmed the existence of dark energy. And yet, we are constructing our entire modern cosmological theory on foundations that have never been empirically verified. This paradox has sparked a wave of introspection among scientists. Some physicists are beginning to ask, are we fundamentally misinterpreting the nature of the universe? Could there be a model that explains cosmic acceleration and unusual gravitational effects without resorting to dark matter or dark energy? These questions are not merely theoretical. They are the seeds of new frameworks, and one of the most daring among them will be explored in our next chapter. The Transient Singularity Theory of Dr. Richard Lua, bold model that could shake the foundations of the Big Bang and completely reshape our understanding of the origin of everything. The flaws in the Big Bang and the rise of alternative models. Although the Big Bang theory remains the cornerstone of modern cosmology, a growing number of scientists are beginning to recognize that it fails to explain every phenomenon in the universe. Some seemingly minor issues have sparked major doubts, fueling the search for alternative models that are stronger, broader, and more coherent. One of the fundamental weaknesses of the Big Bang model is its reliance on an initial singularity. According to the equations of general relativity, when we trace the universe back in time to its origin, the density of matter and energy approaches infinity, the size of space collapses to zero, and the laws of physics break down entirely. This is the singularity point, where modern physics is utterly powerless. But how reasonable is it to believe that the entire cosmos began from a place science itself cannot describe? Then there's the so-called horizon problem. Why is the temperature of the cosmic microwave background, CMB, almost perfectly uniform in all directions, even though the regions of the universe we observe are too far apart to have ever communicated since the Big Bang? To address this, scientists proposed a hypothetical phase called cosmic inflation, a period of rapid expansion in the first fractions of a second after the Big Bang. However, inflation theory itself depends on speculative energy fields that have never been directly observed. Beyond that lies the large-scale homogeneity problem. Why does the universe appear so uniform everywhere, even though the early chaos of the Big Bang should have resulted in far greater irregularities? And there's the baryon asymmetry problem, the unresolved discrepancy between matter and antimatter after the Big Bang, which still lacks a satisfactory explanation. These weaknesses have led to the emergence of numerous alternative cosmological models. Cyclic cosmology proposes that the universe doesn't have a singular beginning, but instead undergoes endless cycles of expansion and contraction, challenging the idea of creation ex nihilo. The emergent universe model suggests that before the Big Bang, there was an eternal static phase, and only under specific conditions did space begin to expand. Meanwhile, string theory takes an even bolder approach, positing that all particles in the universe are not point-like, but are instead tiny vibrating string structures that inherently prevent the formation of singularities. Each of these alternatives offers a unique perspective, but they also come with assumptions yet to be experimentally verified. Amid this expanding landscape, a more radical theory has begun to capture attention: Dr. Richard Lue's transient singularity model. Not merely an alternative to the Big Bang, this theory seeks to reset the entire framework of cosmological thought, discarding the notion of a singular origin, rejecting the fixed existence of dark matter and dark energy, and introducing an entirely new understanding of creation in space-time. In the next part, we will dive into this theory of the most profound philosophical and physical turning points of the 20th century. As the seemingly solid foundations of the Big Bang theory begin to crack under the weight of unresolved paradoxes, a few bold scientists have stepped beyond the comfort zone of the standard model. Among them, the name Richard Lue emerged like a fresh breeze, carrying a daring hypothesis. The universe did not begin with a single grand explosion, but was instead shaped by billions of mini-bangs, transient singularities scattered throughout space and time. Dr. Lue's theory, known as transient space-time singularities, begins with a courageous question: what if we entirely removed the initial singularity of the Big Bang, along with the need for dark matter and dark energy? In his model, the universe doesn't originate from a single event, but rather from an infinite sequence of microscopic bursts continuously occurring within the very fabric of space-time. Each burst is a local singularity, a rapid, fleeting event that generates matter, energy, and a temporary distortion of space-time in its vicinity. These distortions don't last, they quickly dissipate, but together they create a cumulative effect that drives the expansion of the universe. Instead of a static dark energy force pushing the universe apart, Dr. Lue suggests that the accelerating expansion we observe might simply be the result of billions of unsynchronized micro-impulses, brief, chaotic, uncoordinated flashes caused by these transient singularities. Like sparks that flare and vanish, they momentarily illuminate space-time, yet leave behind a powerful collective impact that shapes cosmic motion and structure. What's particularly radical about this model is that it doesn't require dark matter or dark energy to explain the abnormal rotation speeds of galaxies or the accelerating expansion of space. Instead, all anomalies are attributed to temporary distortions in space-time itself, as if the universe's very fabric is alive, constantly stretching, contracting, and self-adjusting. According to Dr. Lue, each singularity is a creative point, where space-time is suddenly compressed and then released, generating not only energy, but also form. These singularities are not ancient relics, but active, ongoing phenomena happening right now, everywhere. The universe, in this view, isn't the product of a singular beginning, but a self-organizing, self-creating, self-transforming system from within. Dr. Lue's transient singularity model is not just a substitute for the Big Bang. It offers an entirely new way of understanding time, space, gravity, and creation. If the Big Bang is a grand opening symphony, Lue's theory is an infinite chorus of fleeting notes with no clear beginning, and no need for a fixed cosmic score. The most important part? This model can be tested. In the next section, we'll explore whether this bold theory can explain gravitational phenomena and galactic motion without relying on invisible mass or dark matter. Gravity without mass, when space-time bends itself. In modern physics, the definition of gravity has become almost canonical. Gravity is the result of mass curving space-time. This is the foundation of Albert Einstein's general theory of relativity, proposed in 1915, a monumental breakthrough that replaced Newton's classical idea of gravitational force with a mesmerizing geometric vision. In this picture, the sun doesn't pull the planet, it bends space-time around it, and Earth follows a curved path as a result. However, in Dr. Richard Liu's Transient Singularity Theory, a bold new assumption is introduced. Gravity can exist without mass. On the surface, this seems to contradict everything we've believed. How can there be an attractive force without a body to generate it? But Dr. Liu offers a different lens. Gravity doesn't necessarily have to emerge from matter. It can arise from local geometric distortions, tiny defects in the fabric of space-time itself. Just like a sheet can wrinkle without anything pressing down on it, space-time with its intricate dynamic lattice can also deform due to internal energetic processes. And each transient singularity described in Liu's model can leave behind a shock-wavy temporary warp in the local structure of space-time that influences the motion of nearby objects, producing gravitational-like effects. In a 2024 study, Dr. Liu developed a mathematical model showing that micro-level geometric distortions in space-time despite containing no mass, can produce gravitational fields equivalent to those observed at galactic scales. This is a groundbreaking insight, as it could explain the puzzlingly rapid rotation of galaxies without invoking invisible dark matter. Instead of hypothesizing the existence of some undetectable form of matter, we might simply accept that space-time is not flat, nor is it uniform. It may contain scars, tremors, or energy folds, and these invisible warps could still guide stars, galaxy clusters, and even shape the ultimate fate of the universe. If this theory proves correct, it wouldn't just eliminate the need for dark matter, it would fundamentally redefine the very nature of gravity. Gravity would no longer be a byproduct of mass, but a dynamic expression of spacetime's internal vitality. In this vision, the universe is not a passive stage upon which matter performs. It is the main actor, constantly shifting, rippling, and composing every motion we observe. In the next section, we'll go even further. If transient singularities can generate gravity and energy, could they also be the true engine behind the expansion of the universe? Might these internal jolts in the cosmic structure be the real cause of the mysterious acceleration we currently attribute to dark energy? The return of negative pressure and the quantum leaps of space. One of the strangest concepts ever introduced into modern cosmology is negative pressure, repulsive force that defies intuition. Unlike the positive pressure we're familiar with in systems like gases or fluids, negative pressure doesn't compress, it stretches. It doesn't resist, it propels expansion. This makes it a prime candidate for explaining why the universe is not only expanding, but doing so at an accelerating rate. A discovery that stunned astronomers in 1998. But the idea is not new. Back in 1917, when Einstein realized that his general relativity equations predicted an unstable universe, either expanding or contracting, he added a cosmological constant to keep the universe static. This constant essentially had the nature of negative pressure. Though Einstein later withdrew it and famously called it the biggest blunder of my life, nearly a century later, with the rise of dark energy, the concept of negative pressure made a dramatic comeback. In the transient singularity model, Dr. Richard Liu introduces a completely new interpretation of negative pressure. Instead of being a background energy field omnipresent throughout the cosmos, it is proposed as a series of ultra-short pressure surges, each triggered by a fleeting singularity event. In that moment, space-time doesn't just warp, it balloons outward, like a bubble stretched in a single heartbeat. According to Liu, the universe doesn't expand in a smooth, linear fashion as previously thought. Rather, it leaps in discrete spatial steps. Each step corresponds to a singular microburst, producing a localized pulse of negative pressure that then fades. When billions of these spatial jolts resonate across the cosmos, they create the illusion of a steady, continuous expansion, when in fact, it's the result of countless asynchronous spasms in the fabric of space-time. This approach not only explains accelerated expansion without invoking a perpetual dark energy foreset, also opens the possibility of tracking these very leaps through astronomical observation. If the universe expands in uneven rhythms, we might detect subtle discontinuities in the Hubble diagram, which charts galaxy recession velocities against their distance. These wrinkles could also leave imprints in the cosmic microwave background radiation or in the large-scale distribution of galaxies and matter. In other words, the universe might be breathing not with a gentle rhythm of a biological organism, but with an electromagnetic heartbeat, where every contraction is a singularity and every expansion a leap in space. If this model proves correct, it would not only remove the need for dark energy, but also offer a testable path forward, something few theoretical models dare to propose. The universe, instead of being an eternal wave of smooth expansion, could be a fragmented symphony where each beat carries the echo of momentary creation. In the next section, we'll explore the observational evidence that could confirm this theory and ask whether humans might one day hear the hidden heartbeat of the cosmos. In science, no idea, no matter how elegant, can survive without testability. This is the gold standard, the clear dividing line between a scientific hypothesis and speculative fiction. And what's remarkable about Dr. Richard Liu's transient singularity theory is this: it is not a philosophical metaphor or a metaphysical speech. It is a mathematically grounded physical modelant. It can be tested with real observational data. The central question becomes, if the universe is not expanding smoothly, but rather unfolding through irregular spatial leaps, each one the result of a brief singularity burst within space-time, then where are the traces of those leaps? One of the first places scientists look is the Hubble diagram, the map of galaxy velocities plotted against their distance. If the universe expands not in a continuous curve but in jolts, the Hubble line might not be as smooth as we've assumed. Instead, it could contain subtle breaks, microfluctuations, or regions of unexpected variation anomalies that the standard lambda CDM model cannot explain. Next is the cosmic microwave background, CMB, the oldest map of the universe, recording light from just 380 years after the Big Bang. If countless transient singularities erupted throughout cosmic history, then the tiny temperature fluctuations in the CMB might harbor asymmetries or unusual cluster aftershocks from those local bursts in the fabric of spacetime. Then there's the large-scale structure of the cosmos, vast cosmic web of galaxies, galaxy clusters, and filaments. If space leaps occurred periodically over time, we might detect zones with unusually dense galactic clustering, or galactic walls, whose shapes defy explanation under continuous expansion models. The good news? Humanity is no longer peering at the sky with naked eyes. With instruments like the James Webb Space Telescope, the soon-to-be operational Vera Rubin Observatory, and supercomputer-based universe simulations, we now possess the most powerful tools in history to probe the very heartbeat of spacetime. What's even more exciting, we don't need to wait millions of years to verify this theory. If Dr. Liu's model is correct, then transient singularities are occurring right now, all around us, subtly warping the spacetime we occupy and leaving imprints in the light and gravitational waves from distant stars. This means every bit of data we collect from the universe, from ancient starlight to ripples in gravity, may hold the clues to prove or disprove this radical model. The question is no longer, is it real? But rather, are we refined enough to detect it? In the final chapter to come, we will reflect on this journey of discovery and pose the ultimate question: if the Big Bang is wrong, what awaits us beyond the veil of the universe? If the Big Bang is wrong, then what awaits beyond the edge of the universe? We've grown used to living in a universe with a beginning, a glorious moment where everything exploded from nothingness, launching a 13.8 billion-year journey. The Big Bang isn't just a physical theory, it has become a framework of thought, a modern origin myth replacing the ancient stories of creation. But what if that beginning never happened? Dr. Richard Liu's Transient Singularity Theory doesn't simply question the Big Bang. It unveils an entirely new vision, a universe that didn't explode once, but flickers into being rhythmically, intermittently, point by point. There is no single origin, only an endless cascade of creation. Matter, time, and gravity don't emerge from a fixed singularity, but from countless transient bursts, subtle quakes in the living fabric of space-time. If this is true, then the universe is not a stage gradually dimming after one great act. It is an ongoing performance, where every passing second is a new scene, a singularity born, a burst of space ignited, then silently fading away. In such a cosmos, existence is not the product of the past, but a perpetual present shaping itself. In this view, gravity is no longer an invisible thread pulled taut by mass, but the trace of deeper vibrations within space-time itself. Negative pressure is no longer an eternal, mysterious force. It becomes the irregular heartbeat of spatial surges. And dark matter, dark energy, the unseen ghosts, may simply be artifacts of an old model still trying to make us think within outdated boundaries. The ultimate question is no longer, where did we come from, but is the universe still creating itself right now, everywhere? We humans, tiny creatures peering into the cosmos through billion-dollar telescopes, may be listening to the invisible pulse of a self-organizing universe. A cosmic symphony composed in geometry, energy, and time. And in that music, we are not merely spectators, we are part of the arrangement. Our thoughts, our curiosity, and our conscious wonder may themselves be a note in this grand orchestra of becoming. The transient singularity theory may prove right or not, but it reminds us of a vital truth, that all truths, even those held for centuries, must be re-examined in new light, and sometimes that light doesn't come from distant stars, but from the courageous questions we dare to ask. You can continue to believe in the Big Bang, and there's nothing wrong with that. But maybe, starting today, you might also imagine a universe that doesn't need a beginning, doesn't need an end, only a moment-by-moment shimmer, a burst of unseen light, creating something entirely new. So, what do you choose to believe? Thank you for joining Astronomy Universe on this journey through bold theories and fresh perspectives on the cosmos. Whether you choose to believe in the Big Bang or open your mind to the transient singularity model, the most important thing is this: we never stop questioning, never stop exploring, and never stop expanding the boundaries of human thought. If today's content sparked your curiosity or challenged your perspective, please like to support us. Comment to share which model you believe in and why. And don't forget to subscribe to Astronomy Universe so you won't miss our next journeys through time, space, and the questions no one else dares to ask. Keep looking up, because somewhere right now, a fleeting singularity might just be lighting up somewhere in the dark. Wishing you a wondrous journey of discovery. See you in the next video.